Welcome back class for the lecture on computer vision. So if you remember last time in lecture 3 we discussed the correlation and we saw how it works, the correlation operator by using the impulse response signal. So we will continue our discussion for the use of correlation. So here we will see some practical uses of correlation. One of those uses we will study today is the templates. So filters we have seen till now. We saw filters, the box filter for example, and then the Gaussian filter. We saw those filters that are used as blurring agent. They are used to remove the noise from the images, and in this process the images also become a little bit blur. So that is the side effect. So here we will see another use of filters. Filters, they can be used as templates. What is it? What are the templates? First of all, we will see an example on the signals. So remember the same thing I repeat many times. We have a signal. We discuss some concept, and that concept then we apply on the signal processing domain, and then the same concept we explain it on the image processing domain. Okay, so here we see the concept for templates. So first of all, let's see there is any audio signal, so any communication signal. So if you see, it is some sort of uh, irregular shaped wave, and on the x-axis we have the time, and on the y-axis it is the amplitude of the signal. So you see over here 0, and then there is some plus range and the minus range. So that is a signal. Now what we want to do is that, for example, in this signal I want to find out a specific pattern. So pattern is given over here, this pattern. So if you look over here, uh, if I try to find it myself, it's not easy to find this pattern in the image, in the signal, in the data. So for this purpose, what we can do is that we can take the signal and the filter. So remember, in this case the filter is also a short signal. Okay, so filter is also a signal, and if you see, the pattern is repeated over so the pattern, which one is it? So it's repeated here. Yeah, it starts, I think, over here. So it goes, then there is a small peak, and then there are two high peaks. So it's a pattern from this point to this point. Okay, so this is my filter. Filter is basically a signal. This signal comes inside our main signal somewhere over the time period. Okay, so what we can do is that, and the purpose is that I want to find out this filter signal inside our original main signal. So what we can do is that we do a cross correlation of these two. Okay, so I take the signal and I take the filter, and if you remember, this is the symbol for the cross correlation. I apply this signal and the filter, we do the cross correlation. It will give me some result. Okay, and when I interpret this result, when I try to observe what the result says, it will give me some values. Okay, so we are not interested in those values, but out of those values, wherever this filter matches the signal, at that place over there, the result of the correlation, it will have the maximum value. Clear? So result of the correlation is somewhere over here, it's maximum when it fully matches. This point matches here, and the rest of the whole wave, the filter wave, it matches with the original signal. Okay, so this is something what we can say template matching. So this normally shorter signal, we also call this shorter signal as a template. Okay, and this overall process is called as template matching. We try to match a shorter signal in a broader main signal, and what we do is nothing complicated. Only take the smaller signal, the template, apply correlation between these two signals, and the result will have the peak value where the template matches. Clear? Now we go and we will apply the same thing on the image. Okay, so let's say this is my main signal over here, and this is my template, smaller signal, the filter. So if you see this filter over here, it is part of the original signal, so it is I think this part. Okay, so when we take it, so let's say you have two signals. So when you try to do it, the correlation, so in our case, uh, here just ignore this code because this is MATLAB code. So MATLAB we don't cover. Okay, we do it in Python. So ignore this code, but we will be using the lab command. We will see in the lab filter 2D. Okay, so we will apply the filter 2D between these two images, and we will get some result where there will be a peak value at the matching point. Where the two images match, there will be a peak value in the result. Clear? So ignore this code. Code we will cover in the lab. Only focus on these images. So there will be a peak value. So here is another example. This is more simpler example to help you understand. So here if you see, there are three shapes. So shape 1, 2 and let's say 3. And out of these three shapes, the template matches to shape number 3. Okay. Don't get confused with the size. Practically they will be of the same size. Here it's just looking a little bit bigger, but practically they are same size. Okay, so the template matches with the third image, and when we apply the correlation between these two, the result will be something like this. You see over here on the right side, this is the resulting image. The result of the correlation of two images, one the main image and one the template image, it will be something like this. So there will be black, dark and bright spots. So wherever there is a little bit of matching, for example, remember the template was in black color. So these shapes 1 and 2, they are also black. So there is a little bit of matching. So little bit of brightness here and here. Okay, but where there is the maximum brightness, you will see the brightest point. Clear? So this brightest point shows that this is the maximum matching point in the whole of the two images. Clear? This image that you see over here, this is also called as correlation map. So it's called correlation map. So we take a template or a mask and we apply it on the image, and based on that correlation map, then we can easily draw a rectangle around the shape. This is what we will do in the lab. Okay, so you already, if you remember your lecture, over there we used to draw rectangle or circle, so that things will help over here. So we use the correlation map to identify the shape. For this purpose, there is a very typical example that is taught in almost all the courses of computer vision. That example is very typical for this course. It's called Where is Waldo? So the example says that you are given a big picture with maybe hundreds of characters in the image. Okay, so there are hundreds of characters in the image, and out of those characters, one character is our desired character. So that is our template. Now what we want to do is that we want to find out this template inside the main image, which is called as scene. So scene is the main image, template is our target. Now you will see the advantage of computer vision. Remember in chapter 1 we said that computer vision is better than human vision in some repetitive tasks. So here is one such repetitive task. If I want to find this template inside the scene, the human eyes cannot find it easily because there are hundreds of shapes or characters. For this purpose over here, computer vision is more superior. Computer vision can find it more easily. So that's the task. You just pause the video, try to check if you can find this template inside this whole image. Okay. So for this purpose, we use the template matching. We just correlate the two images, and based on that correlation, we can find in the correlation map, we will find a bright spot, and we can use that bright spot to make identify and circle the target. So here is the correlation map. Out of all, there were a lot of images, so there will be a lot of bright spots, but the brightest spot is over here. Now this is a very big problem, that this brightest spot, it's not easy to identify with our eyes only. For that purpose we will be using programming. Okay, we will not rely only on our eyes, because maybe there are some other spots, maybe our eyes feel that they are also bright. So for this we will use programming. So we take the correlation map, and then that helps us to find the template in the scene. Clear? So in the lab part, we will be using this Waldo, but a different image of Waldo, and we will see how to find it out. So there is a quiz now. What do you think that this method that we have used over here, will it work for finding the Waldo in the most of the situations? So take your time for this quiz. We will come back to this quiz. Now let's go back to the lab side. Okay, so open the lab. So lab number 4, it is about 2 parts. It has 2 parts, templates and edges. As usual, load the 3 libraries, and then we see over here the template detection. So all these things that you see, the Waldo image is given in our images folder. So here you see, now you are more familiar with your commands. So first command over here is to load the Waldo image. So this is the waldo.jpg. We store it in a variable called scene. So this is the scene. Okay, remember this Waldo that you see over here, this example, it is not the same as in the slides. Slides has a different one, this one is different, so it's not in the same place, it's not here somewhere. Okay, so I load it as a 12 by 12 figure. So the figure size is specified 12 by 12, and then I display the scene as a grayscale. So remember, in our images we never use color images. In our codes we never use color images. This is over here we load them as gray images, grayscale layer. So that was the first part, load the scene. Second part is load the template. So template is another. It's saved as an image called as Waldo underscore query. Query means question. Okay. So remember from your database, SQL is structured query language. So query itself means question. So this is the question. You have to find this image inside the scene, somewhere in the scene. So you can just imagine how big this task is. So it's a quite a problematic task. It's not easy. You will take literally minutes or maybe hours to find this image by your eyes only. Okay, so these are the two steps: the scene, loading the scene, and loading the template. Then what we do is that there is a function given for this. Okay, this function will automatically do the correlation. Okay, you can, if you want, you can also apply the filter 2D, but there is a function here. It's called CV2 match template. So match template is same thing. Over here it has three input arguments. You will provide the scene, you will provide the template, and then you will provide a constant. The constant is basically the CV2, this constant, we will provide it a coefficient for transformation. The coefficient for template matching. So we will give this constant to it directly. So remember, if you remember, we discussed this thing, I think, in second lecture somewhere, that the constants are also provided in CV2. And normally the constants, they start with the name of the function where they are used. So for example, in CV2, the template matching constants, they start with tm underscore. So tm underscore, and then there is c coefficient. Okay, so when you apply this, the result is over here. This is the result, and if I plot this result, it is a huge image like this. Now again, this is a big problem. The matching points of the correlation of two images, it will result in an image with a bright spot. But again, finding this bright spot with our eyes only, it's not easy. Okay, so when it's not easy to find that bright spot, for that purpose, again I will use programming. In the programming in CV2, there is a function, another function, very, very important. It's called as min max locator. Min max locator, what it does, so if you want, I will go and I will search min max locator. So right over here CV2, and then over here write min max locator. So the first one, so opencv.org, the first one. So I would like to see, so these examples are for C++. Now Python is there. So let's see. So there are lots of functions on the side. So min max loc, you see here, click on this, it will open this. So here it shows that this is the function cv2.minmaxLocator, and you will give it one or two values. So one value is the source image, and the second value is a mask, which is optional. So we give only one value. So the function, what it does is, you provide it an image, and for that image it will give you the two pixels, the pixel with the minimum value and the pixel with the maximum value. So first of all, it will return to you four values. Four values will be returned. Remember, Python programming is different from C++ and Java. In C++, Java, you can only return one value. Here in Python you can return multiple values, no problem. So you return over here 4 values: minimum value, maximum value, and the location for the minimum value and location for maximum value. So for us the location is more important. I am not interested in the minimum or maximum value. Minimum value maybe it is 0 or maybe it is 1 or 2. Maximum value can be maybe 255 or maybe a little less, 254 or 250 or maybe even 200 depending on the image. But for me the interesting thing is where this value occurs inside the image, in the scene. That is given by max location. Clear? So this is what I want to use. So 4 values are returned. I only want to use 1 value. So here it is. When I call this function, it will return me 4 values. In Python, you can do like this, that if the function returns 4 values and you don't want to use any value, you can put an underscore just to show that I don't want to save this value. Okay. So I can write over here A, B, C also. For example, A, comma B, comma C, and then I can write D. Okay. So just I show you. For example, if I write like this, A, B, C, D equal to CV2 dot min max locator for this result image. Now what will happen is that out of this image, the A variable, when I run this command, the A variable will contain the minimum value, B will contain the maximum value of the pixel, C will contain the location, the XY location. So it will give the location like this, like using in the shape of tuple. So the location will show the C location. C variable will contain the location for the minimum pixel value, and D will contain the location for maximum pixel value. So instead of declaring variables that I don't use, so for example A, B and C, I will not be using them. So why should I declare them? It's a waste of resource. So instead of writing ABC, I just write over here underscore. So underscore, underscore, and underscore. Clear? So this is how I will be using only one variable. Others 3, I just ignore them. So here, now come back to this command. So I delete this, and in my command I save the location for the brightest point. I call it the top left. Why I call it top left, you will see in the future. Okay. So the top left, so if you go back to the lecture, the template, when I try to find it, the maximum value that it will return, it will be the top left corner of this template. So it will return me this location. Okay. So to find out the full rectangle shape, how I will draw the shape, I can just take the top left corner, and I can, from there I can draw the rectangle which has the shape of this template. Clear? So top left corner in this is 100, 569. So 100 is for example on the x-axis somewhere here, and 569 is on the y-axis. It will be somewhere here. So 100, 569, if you see, it is this bright spot. Okay, clear? So this is it. When I have found the brightest spot, this is the starting of the rectangle. Now how should I draw the rectangle? For this purpose, I will add the shape of the template. on this rectangle. Okay, so let me run these commands. So it will take some time. Remember, the template has got a shape. Remember, the template is given over here. This is the template. Okay, so this is a template which has some dimensions. For example, here I think it has the height is 40 and the width is I think 12 or 13. I don't know what it comes. Here it is. So if you type the command template, so template is the name of the variable. You type it template dot shape, it will return 40 comma 14. So height is 40 and the width is 14. Okay, so starting from this point over here, 400 comma 569, you want to draw a rectangle which has the height 40 and the width 14. Okay, so using these two values, I find out the bottom right corner. So the top left corner, so remember, top left is 100 comma 569. So what you do is that you do 100 plus, so 100 is on the x-axis, so 100 plus 14, and on the y-axis you will do 569 plus 40. So it will give you the new value. So it will be the new value. The bottom right corner of the rectangle will be 500 and 609, I think. Okay, so the bottom right corner is found like this, 114 and 609. How it comes like this? It is based on this calculation. I am doing over here just one simple thing. The top left variable, its first value, so when I write 0, it means the first value, which is 100. I add to this value the template dot shape, the first value, and the second value. So in the template dot shape there are two values. There is 14. So I want to add this 14 to 100, and I want to add 40 to this second value 569. That's what is happening over here. Top left 0 and template dot shape 1, we add them, and top left 1 and template dot shape 0, we add them. It will give me the bottom right corner of the rectangle. Clear? So this is it. With these two values we can easily draw the rectangle. So remember, the command was cv2.rectangle. If you don't remember, go back to that lab and you will see over there that the cv2.rectangle, it requires a scene, and you need to provide two more things, the top left corner and the bottom right corner of the rectangle. That's why I created these 2 points over here. So top left and bottom right corner, we make it, and then I give it the color which is white, and then I give the thickness of the line. So when I draw it, it is this over here, the shape. And if you look carefully, this is the same Waldo that I wanted to find in the scene. Clear? So this was your task. This was your lab for today. And now coming back in the lecture. So here in the lecture slides, the template was this thing, and it was inside somewhere over here in the scene of the Waldo. Clear? So coming back to the quiz, what do you think this method will it work for finding Waldo in most of the situations? Yes or no? So it can be possible that we can use it, but one important thing for this approach is that you must have, for example, you must have the exact value or exact shape of the template that you want to find. Okay, so you must have the correct shape of Waldo, then you can find it inside the scene. What do you think? Do we have such a shape available in natural situations? No. Why? Because, for example, let's imagine you are sitting in the classroom and the computer vision algorithm wants to find out the chair, a specific chair in the classroom. Now the problem is that the shape of the chair will change based on the angle of chair in front of the camera. Okay, if the chair is just in front of the camera, the shape will be different. But if you move the chair a little bit to the side of the camera, the shape of the chair will change totally. So that's the problem in such cases where the shape of the template is changing or it's not fixed. You cannot use this thing efficiently. So practically for this quiz, the answer is no. Now we can't use this method very frequently because we don't have the right template. Clear? Same is the case. Even if I have a photo of a person, I cannot use that photo of that person to find him inside a big crowd because the shapes will not match based on the person's orientation. If the person is shown in the scene from a side pose, it is not same as the person shown in the template from the front. Clear? So it's not so practically useful. This approach is only given here for theoretical basis to make you understand the use of template. Practically it's not used. Here is one more example. There can be little bit of help, but it's not perfect. For example, if the template contains some sort of car shape, okay, then the scene contains some big vehicle like an SUV or a Jeep, and the template contains a car, it will still show some sort of matching because the image contains only one car. That's why it will show you easily the matching because there is only one vehicle here. But if there are tens or hundreds of vehicles, then it will be a big problem to match them because they are not same. Okay. The matching that is occurring in this case over here, it is because both the vehicles have a general structure which is similar. For example, both of them have two tires shown. Both of them, they have a door or windows. Clear? So if the template is not identical, it's not easy to find the matching, but still it can work to some limits. So it can find out the template. Clear? So the summary is that we can use the filters to localize or to find out some interesting areas inside a big image. And this, how we do this? We do it by looking at how well a filter responds to different locations, where the filter is giving the best or the brightest value. So till now we have seen the use of filters both to do the noise removal and also over here to find out some template matching. In the future, we will be seeing some other use of filters like edge detection. So this was your lecture and the lab together. And there is a small assignment over here. You can see assignment 5. It gives you the same things, the names are given. So here you have a scene. It's called tablet.png, and in this scene you have to try to find out the template.png image. So template is a small image. You have to find that image in the main image, which is tablet.png. You will do all these steps. The steps are given. You have to write down the code, and you will do all these steps until step number 7, and finally you will make a rectangle around the image. Do these assignments, do this lab work more carefully, because remember, all this will be part of your exam. Clear? So I wish you good luck for this task. Last date for this is 24th. It is not extensible. Remember one more thing. So okay, we will discuss it in another video. So that's it. We finish it over here.